Welcome, welcome. We're excited to be here. Another recording. Yay, physics. Okay, I'll stop now. In previous recordings, I sort of hand waved my way around the issue of the electric field vectors and what I call electric field lines point. And I'm going to pause for a second. Okay, sorry about that interruption. So as I was saying, in previous lectures, I hand waved my way around the issue of the direction that electric field lines and electric field vectors point. What I want to do now in this lecture is finally fulfill that promise that I made a few times and go through the direction of electric fields in a more systematic way. I'm going to actually do it two different ways. First one mathematical, and then the second one sort of conceptual. And the starting point for the mathematical approach is Coulomb's law, written in this nice, compact, simplified form. The idea here is that you get source charges, they create an electric field. Then you place whenever you get around to it, which could be days after you've created your electric field, who knows. But whenever you feel like it, having established your electric field, then you stick a test charge somewhere in the field. And as a consequence, the test charge will experience an electric force. And the magnitude and the direction of the electric force is given by this simple relationship, and the hard stuff is calculating E in the first place. Well, again, from a mathematical point of view, you can see that the direction of the electric field and the direction of the electric force have to be the same, sort of. What do I mean? Well, the test charge is just a scalar, and so it, under ordinary circumstances, doesn't affect the direction of the electric force. And if you multiply this with this scalar, then the resulting vector here has to point in the same direction that this vector points, and that's been true for every vector that you've ever studied, and it's still true here. The one place that we have to be careful, and I'll come back to this, but the one place we have to be careful is if your test charge to be a negative charge, in which case there'll be a negative attached here to capital Q, which would then attach a negative sign to the right-hand side, which would then necessarily indicate the reversal of the direction for F. In other words, if E pointed in, let us say, the positive y direction, then the force on a test charge, on a negative test charge, would then point y direction, okay, because the negative charge would bring along its own minus sign. Now, I hesitate to explain it that way because I've told you already several times that you never insert the negative sign when you actually do calculations, and so that's true. But that was sort of the easiest way to get you to start thinking about this mathematically. So there's that. So that's pretty much all the math that I want to say about it. Now let's think about it physically, and specifically, let's think about a field of a source charge without any reference to the test charge at all. So I think I'll just erase this. I want to say that the concepts that I just gave you about the relationship between the force and the field, while everything I said is correct, it is not normally the way we think about determining the direction that the electric field of the source charges points. It is a true statement. It's something that you should understand, but what I'm going to tell you now is really the way we think about the definition or the determination of the direction of the electric field of the source charges. And it simply is this. key idea here is that the direction of our electric field is simply a definition. It's not built into or of necessity from how the field works or how or anything else like that. It's simply a choice that we made, and then everybody agrees to abide by this choice, and then we're all talking the same language. So again, I need to emphasize for this to make sense to you, and I need you to really understand that there's no charges around at all. Anytime I talk about charge for the rest of this lecture, unless I explicitly say otherwise, I'm talking about the source charges, the source of the electric field. Okay. The definition is that the electric field of a source charge or a collection of source charges is that E, the vector E, points in the direction of the electric force that the electric field would apply on A, and here comes crucial word, the force that electric field would apply on a positive test charge, if there were one, which there usually isn't. In other words, you get a bunch of source charges, some positive, some negative, continuous charge distribution, collection of individual point charges, doesn't matter. You get together a bunch of source charges. They combine to create some net electric field. At every point in space, the electric field has its vector everywhere. Okay? At any random point in space, at every point in space, what direction does the electric field point? The answer is, imagine if you put a positive test charge at that point. Then whatever direction the force on that test charge would point, if it were there, by definition, that is also the direction that the electric field vector points at that particular location. Okay? So let's see a few simple examples of that. We'll get, I'll start with a simple example, and we'll get increasingly. And we will start, as always, with the simplest possible source charge, a single point charge. Okay, so I put a positive charge at some position in space. The essential idea is this. If I were to put a test charge somewhere, let's say a random place here, so there, okay? So capital Q would be a test charge. Then the force that it would experience would have a direction that is parallel, in fact collinear, with the imaginary line joining little q with capital Q. And since our test charge is assumed to be positive for our definition, then capital Q will be repelled from little q, and so at that location, the force that it would feel would point like that. And so, as our definition, or from our definition of the direction of the electric field, then the direction of this force is also, by definition, the direction of the field at this point. And it doesn't matter on this field line I put capital Q. No matter where I put it, the force on it would always point on this way, and so therefore, by definition, the direction of the electric field of little q is also pointing that way. All right? So instead of the force, I say that's the direction of the electric field. And the argument that I just made would be identical if I put my positive test charge there. The force on it would point this way, and therefore the field on it, the field at this location in space, must point this way. Okay. And same is true anywhere along this line, and anywhere along this line, anywhere along this line, this one, or indeed any line that you draw there. And so in short, the reason, first of all, that the electric field lines point radially away, or point in the radial direction, is because every point in space looks the same from the point of view of the source charge, and so the force and therefore the field that creates the force should look the same at every point in space that's equally distant from the source charge, and so the field is kind of nice and uniform in this way. And again, points radially outward. Why? Why outward? Because if I were to put a positive charge here, or if I were to put a positive charge here, or a positive charge here, at every one of these, or for that matter here, at every one of these places, the force on it would point outward, and so our definition of the electric field direction says whatever direction the force on a positive test charge would point, the electric field that is in fact there must also point, is defined to point in that same direction. Okay? Second example is exactly what you probably think it is a negative point charge. I put a negative source charge there, then I ask the question, okay, if I were to put a positive test charge into this negative charge, what would be the direction of the force that such a positive test, if I put it there, which I'm not going to, but if I did? And the answer is, of course, a positive test charge would be attracted to the negative charge no matter where you put it. And the force vector will always point radially or directly toward the negative source charge, and therefore the field vectors, or more correctly, I'm sorry, the field lines, will look, as far as their spatial distribution, they'll look just like the field of a positive point charge, but because a positive test charge would be attracted to the negative source charge, then our definition of the direction of the electric field says that the electric field must point radially inward. Now, I've drawn these pictures before, but now I'm explaining why I put the arrowheads in the direction that I did. Okay. I'm about to give myself a headache because I'm going to do a dipole, but I'm going to draw it in the reverse way that I have always drawn it for my entire life. And this is probably going to make my head explode. But anyway, third example, field of a dipole. Okay, so the field of a dipole, sorry. So this is a dipole. Remember, a dipole is two equal and opposite charges that are close to each other. So I've drawn this before, but now let me kind of walk you through it. Choose any random point in space. So again, our goal here is to not only construct the electric field, but also to determine the direction that the field lines point. Right. So you choose a point in space. So random point in space there. And so then I ask the question, what direction does the field point at that location? Well, of course, there are two fields at this location. One at this location, there's a field from the positive charge and another field from the negative charge. And so we analyze this. The first thing that leaps out at us is that the positive field, if I can call it that, is going to be larger, that is to say, have a larger magnitude than the negative field, because we're farther from the negative than we are from the positive. Second of all, the total field is going to be the superposition, the vector sum of these two fields. And third of all, the rule holds. The direction of the field for each one of these charges is determined by the direction of the force that they would apply, that their field would apply on a positive test charge. If I were to, you pretend that you put a positive test charge there, figure out the direction of the force that test charge would experience, and then say, okay, whatever that direction was, that's the direction that the field points as well. All right, so if I were to put a positive charge here, it would be repelled away from the positive charge and fairly strongly repelled because it's comparatively closer to the positive source charge than it is to the negative. So therefore, we will have a strong positive field up there. Well, E positive, I guess. Meanwhile, the negative charge will attract our hypothetical positive test charge, which isn't there and isn't going to be there, but it would be somewhat attractive that way. Let's probably draw it something like that. And so now the vector at that point is the superposition of these two. And so remember from early days of 114, I'll do graphical addition of vectors, and I'll take this field vector and I'll move it tip to tail with the positive field, that's E minus, and then the net field at that location, I guess I'll do it in brown, is drawn like that. And so that last vector then is the direction of the net field at that location. Okay. And I could do exactly the same analysis at some other random point, let's say there. At this location, a positive charge would be strongly attracted to the negative charge. It would be strongly repelled from the positive source charge, and therefore, at this point, which I've sort of intended to be halfway between the two source charges, then the net field there, I hope you can see that the vertical components will cancel, and at that point, the net field is going to point horizontally and to the left. So that's the net field there. Down here, again, halfway between, it would be the same argument sort of in reverse. So positive field would point this way, negative field would point that way. Again, their magnitudes would be equal because we're equidistant from the two charges, so the net field is going to point like that. A little bit larger magnitude here. So that's the net field now. Anyway, it's not my purpose to construct the entire field from first principles. I've drawn it for you before. I've shown you how you think about it. And so I'm going to fill it in. We like dipoles because they're nice and symmetrical. There. After you've done this every day of your life for a million years, you tend to get a little bit sloppy. These, and I shouldn't, since this is perhaps the first time you're seeing this. Okay, and just a couple of things I want to point out. First off, as I say, I'm being a little bit sloppy. Really, all of these field lines should be starting anything at these charges. Specifically, all of these field lines should be starting at the positive charge. So they should all attach in your drawing to the positive charge, like so. And they should all end and attach on the negative charge. They shouldn't stop in midair the way I did. Okay. Another thing that you want to be careful of, and we'll go over this in the next record. There's some rules for drawing these field lines correctly. There's some things that you must always do and some things you must never do. So, like I said, I'll do that in the next recording. But the thing I want you to get out of this diagram here is, once again, the direction that I assigned all of these field lines is determined by the rule. If you were to put a positive charge there, what would be the direction of the net force on it? And I claim it's going to be like this. Let's take a look at it. So this point in space here. Now, according to my drawing, the prediction is this field line pointing this way suggests that the force on a positive chest charge, if I were to place it right there, the force on such a positive chest charge would point kind of upward like this, almost but not quite vertical. Let's take a look, see if that makes sense. At this point in space, we are very far away from the positive charge, so a positive test charge placed right here would feel a very weak repulsive force, and therefore the field at this location is very weak and pointing away from the positive charge. Meanwhile, the negative field, well, a positive charge placed here would feel a strong, or at least comparatively strong, force that away, and therefore the negative field points that away. And so, once again, I'm going to vector addition, move this positive vector up here, tail to tail. Right? And then I will draw the vector sum of those, and yeah, I wasn't far off. Okay, so should be up a little bit more like that. Okay, so perfect. And so that's how you think about it. Bottom line, the direction of the field is defined as the same direction as the force that the field would apply to a positive test charge, and that idea is applied to every point in space. All right, so there's that. Next recording, we'll go into the other concepts that I want to deal with electric field line diagrams, which is how do you draw them, what must you always do, what must you never do, and what information can you glean from them, and in particular, what in the world happened to the magnitude of the vector and the length. So we'll deal with that in the next recording.